happens when things roll and slip, essentially. So that's one of the things we want to cover with you today.
You videoing?
I is.
So we've got this thing here, and as it rolls without slipping, right, it just kind of goes forward and rolls like that. But if it rolls with slipping, it essentially slides a little bit, slides a little bit, slides a little bit, rolls, slides a little bit, rolls. Like that. And so the analysis can be much more complicated than we might otherwise think about. So, here we go. So the first thing that we probably want to cover is what does it mean to not slip as you roll? Okay, any thoughts? Yeah, Tammy.
Well, if it doesn't slip as it rolls, is the coefficient of friction, like keeping the force or equal to the force or greater than the force?
So it definitely deals with the coefficient of friction. If we get going too fast, that friction isn't able to handle it, essentially keep us, it's the friction that keeps us rolling. And so if we go too fast, then that's when that's what causes us to slip. So friction is definitely involved in it.
Does that mean the bottom point isn't at rest?
Okay, so something maybe about the bottom point there.
Ugh.
Yeah, Ashley?
Like horizontal distance it travels isn't the same as when it's just rolling. It's like moving also that way.
Yeah, so when it slips, essentially, right, the horizontal distance it travels isn't the same as essentially the tangential part around there. Because as we roll without slipping, for every one rotation I get, I travel essentially the circumference of this. There. Any other thoughts on what it means not to slip?
Not.
Okay, yeah, so something about, so if the distances are the same that they travel, then the velocities are going to be related to each other.
True.
And so it relates back to that weird thing and about that point at the bottom.
Right.
So a lot of the things that we said about it not slipping, that if you go through it and think about, those are valid descriptions. But oftentimes a very helpful description is that the definition is essentially that the velocity of the point at the bottom is equal to 0. That ultimately ends up being the most helpful definition of rolling without slipping for this case. Okay. So remember, the velocity of any point is the vector sum of the velocity of translation, essentially moving this way, plus a certain amount of velocity as it rotates itself. So the velocity, you can think of any point along here as the velocity, the translational, or you could call it the velocity of the center of mass, plus whatever velocity you get because of rotation. So rotation, or you can call it tangential velocity. Because we talked and we looked about, right, as the piece, and we looked at a point, and it ended up going like this, right? There. Why does it end up doing this kind of weird thing? There, it's because part of the velocity is pulling it backwards, part of it's kind of pulling it forwards, there, along the path. So, if we talk about rolling without slipping, being if that the velocity for an instant at the very bottom and that point is 0, then that tells us something about the relationship between the velocity of it sliding this way and the velocity of the point as it's rotating about. And that's essentially, if this is 0, you get that the translational velocity, or of the center of mass, is equal but opposite to the tangential velocity. There. Now remember, I've put the arrows above there to highlight that these are vectors. So oftentimes direction will matter. Sometimes it'll end up that the direction doesn't matter. And so this is kind of where we start to figure out with rolling and rolling without slipping and rolling with slipping is, can I get an expression for the translational velocity? Can I get an expression for the tangential or rotational velocity? And then that's kind of our plan of attack. So, how should we do that? Where should we go? What should we look at? Okay. Any ideas? I mean, we've studied like a bunch of different things, right? Just throw something out there. Okay, energy. So we could think about doing an energy. Okay, we could use torque.
Forces and torques.
Forces.
Kinematics.
Yes.
Right? Because kinematics have velocities in them, don't they?
Rotational motion.
Okay, we need some probably rotational motion in there. So honestly, as I'm trying to figure out a problem like this that I'm not sure that I haven't encountered before, this is what I do. I draw it out and I just start throwing concepts up on the board and say, okay, fine, what might help me? And then I kind of go through and see what ends up helping. And sometimes one of these end up helping, sometimes they don't. That's where experience comes in. So I'm going to tell you that energy is not going to be as helpful with this because we're going to lose energy due to friction, and we're not exactly sure. We don't have a great way to figure out the actual distance, right? The work done by friction is the force of friction times the distance, but right now we don't have a great way to figure out d, the distance. So that way is not going to end up being very profitable for us, or it'll end up being harder, should we say. You can ask Mr. Sutherland.
Yeah,
we were working on this together.
I didn't finish the energy way. I wanted to, and I didn't, because it was hard.
Okay, and so it turns out that we'll need to use all 4 of these things to really help us get an idea. Okay, so which one of these do you want to start with?
Torque.
Torque. Okay, fine. Let's do that. So, where do we go with torque?
Circles. Friction.
Okay, we go with circles. Something about friction, right? So, we know that the sum of all the torques is equal to what?
The moment of inertia.
Moment of inertia times the
Alpha.
angular acceleration, alpha. Okay, so what torques are acting on this thing?
Friction.
Okay, you got the force of friction,
And that's it.
and that's it.
Yep.
There. You do have other forces acting on it. You've got gravity, but it acts towards in the center of mass,
Yeah.
essentially. So the lever arm's 0.
Yeah.
Same thing with the normal force. It acts essentially through the center of mass. Its lever arm is 0. The only force that doesn't, in this case, is the force of friction. So the torque of friction is essentially the force of friction times the radius of whatever it is that's going through, and then we get I alpha. Okay? Can we go any further from this? Yes?
So would that be, I guess it would be positive because it's helping it to rotate, right?
So, we do have to be very careful with our signs with this way. So you have to pick directions. There, normally we talk about things that are clockwise or counterclockwise. So let's talk about our sign conventions that we want to use here, okay? So we've got this thing, it's rolling this way, okay? As far as the rotation, which way do you want to call a positive rotation? Which way do you want to call a negative rotation?
Clockwise is positive.
You want to do clockwise as positive?
Makes sense.
Okay? Normally it's the other way around, because as you go, if you think about the unit circle, right, the angles increase that way. But we could do clockwise as positive if we wanted to. So what way do you want to do it?
Counterclockwise, like especially if it's
Counterclockwise is positive?
if it's how you circle works.
Sure.
Okay, sure. So we'll talk about counterclockwise as positive. So it's rolling this way, and counterclockwise is going to be positive. So we ask ourselves, force of friction here, is this going to help us go clockwise, or is it going to help us go counterclockwise?
Well done. Good job.
Okay, well, what direction is friction acting? That way, right here. So it's going to help us go what way?
Clockwise.
It's going to help us go clockwise. That kind of makes sense, right? Because the force of friction would be negative. So essentially our angular acceleration would be a negative angular acceleration.
Agreed.
Okay, so we got that. Now what? I don't know. So when I go as far as I can with one approach, I say, okay, fine. I don't know what to do with next. Let me skip to something else. Okay, where do we go? Where should we try next?
Forces.
Okay, let's take a look at forces. Okay, so we know that the sum of the forces is equal to mass times acceleration. So, let's do it in the x direction. So, what do we do now?
Gotta find out what forces are acting.
Okay, so what forces are acting on it?
Friction in the horizontal.
Okay, we've got the force of friction going back. We've got gravity coming up.
Normal force.
We've got normal force.
And you have the mysterious force of God that is pushing it forward.
Otherwise known as inertia, which is not a force. So this is it.
I meant what I said.
Here, right? So if we do it in the x direction, essentially we get that the force of friction is equal to the mass of the object times its acceleration.
Of course.
Okay? Can we do anything more with this?
I'm sure we can.
Okay, we can solve for acceleration. Acceleration is equal to the force of friction divided by m. Can we do anything else?
Simplify by just writing it as u times g.
Okay, so because we're moving here, we're rolling and we're moving, we know that what kind of friction is there going to be? Kinetic, which is always equal to mu times the normal force.
Yeah.
So in this case, I think you can pretty see that these two will be equal to each other. So the force of friction in this case will be mu times the normal force. Yes.
Did you say kinetic?
In this case,
Is it slipping?
We're slipping.
Oh, okay.
Yes, it's kinetic friction. So mu times the normal force, which is mg, divided by m. Oh, look. Acceleration is just equal to mu g. But now we need to be careful. What direction is our acceleration?
Negative.
It's negative, right? Because our force of friction is going to be negative. Okay, can we go any further with this way?
Probably not. or yes, we can, of
change
course.
the acceleration to terms of the alpha acceleration stuff yet?
We can't quite do that yet. That's a great idea. The reason why we can't is because we're slipping. And so oftentimes we've done this, right? A is equal to R alpha, but that's not true when we slip
Oh.
necessarily. So we won't be able to do that yet, which is why this ends up being such a complicated thing. Okay, any other thoughts about where to go? Okay, we seem kind of stuck here. So we've checked torque, we've checked forces. What next?
Rotational.
Okay, kinematics.
We're just
All right, so
it's rotating.
kinematics here.
While it's slipping.
What are we going to use? What's going to help us?
Probably angular and linear velocity.
Okay, so maybe look at an angular and a linear, because maybe that can help us bridge the gap between angular acceleration and linear acceleration and what we ultimately need to get to, which is velocities. Okay, so what equations are going to be helpful to us in our kinematics?
V final is equal to V initial plus acceleration times time.
Okay, so we get V final is equal to V initial plus acceleration times time. Ooh, I like that, because it helps us know the velocity at any time if we know acceleration, which we can find here. Ah, I'm starting to like this because I'm starting to see connections between the approach I was using before and where I'm going. Okay, so this is likely a very good candidate for kinematics. So what can we do with that? What can we do with that?
Flip it around so the software
Acceleration, what acceleration?
the acceleration.
That acceleration, right? So we can just plug it in right there. So essentially we can take it to V final is equal to our initial velocity minus mu g times time. Hey, look at that. We came up with an expression for which one of these? The translational center of mass one or the tangential? Translational. So hey, we're halfway there. We know that the velocity here, when we eventually roll without slipping, ends up being right there. Great. Now we need an expression for our tangential velocity. So how are we going to do that? Okay, rotational motion. So let's look at we think about what rotational motion stuff do I know?
Acceleration is, V squared over R.
Okay, so centripetal acceleration is equal to V squared over R. That's if like the whole thing's going in a circle rather than rotating. So that's more like circular motion rather than rotational there. And so we throw that, we say, oh, maybe that doesn't quite work. Okay, fine, that's all right. So, what's our rotational equations that we can bring to bear here?
Velocity is equal to the angular velocity times the radius.
So, we know that the velocity is equal to the angular velocity times the radius. The tangential velocity. Ooh, I'm liking this even more, right? Because now we start to have a center of mass translational velocity, and now we've got something for tangential. Here, this is all stuff we can use. Unfortunately, we've got this omega thing that we don't really know what to do with yet. So where can we go to figure out about omega? Kinematics in particular, rotational kinematics. So we go through which of those rotational kinematic equations might help us with this omega thing here.
The exact same as we already had.
The exact same ones as we already used there, right? Omega is equal to essentially omega initial plus alpha t. And you know what? I'm liking this a lot too, because now I can see a connection between here and what else did we do? Here, with the torque stuff. So if we come back and we say, all right, the force of friction is mu times the normal force r, and that's equal to I alpha, can we rearrange this to get rid of alpha here? Absolutely. So we get alpha is equal to what?
Force of friction times mu.
So essentially negative mu mg over r, negative force of friction, divided by our moment of inertia, I. Which, depending on what's actually rolling, could be 1/2 mr squared, it could be 2/5 mr squared, we don't know. That's why I'm leaving it just as I, because I haven't said what's rolling yet.
Yeah.
Okay, so what do we do with this thing here?
Plug it in.
Plug it in over here. So I get omega is equal to my initial plus a negative, so I'll just make it a negative there, mu m g r over I times t. Okay? Now what am I going to do with this? Multiply it over there by r, essentially plugging it in here. So I get velocity tangential is equal to omega I times r minus, and I'm running out of room, minus the mu mg over I t, right? We have an r there, we're multiplying by r, so it becomes an r squared.
Get your R squared.
So now we've come up with an equation for the velocity because of rotation at any time using stuff that we ought to be able to know. The radius, the dimension, the initial velocity, coefficients of friction, kind of constant stuff there. All right, so notice here we haven't said anything that we're actually not slipping yet. So this is true when we're slipping, this is true when we're slipping. So what happens? Well, eventually, right, you've gone bowling, yes, right? What happens when you initially throw the ball down the lane? What does the ball do?
It skips.
It just it skips, doom, 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 right? But then eventually it slides,
Yeah.
right? And then all of a sudden, as if by magic, what happens?
It starts rolling.
It starts to roll. Why is that? Friction. So what's friction doing to it as it slides down?
It's countering whatever. I don't know.
So what's friction doing as it slides down? It's causing an acceleration backwards,
Yeah.
which causes the velocity to do what?
Decrease.
Decrease. So right now we're decreasing our velocity little bit by little bit by little bit until our force of friction can take over and get enough torque to get it to start rotating. So that as we slow it down enough, eventually then the friction can kind of catch up with the thing and get it to start rolling. And at that point, when it starts rolling, this is true. here. The moment we start rolling without slipping, this is true. And guess what?
Then we can use.
We've got that equation, and we've got that equation there
Cool.
that we can plug in
So you can essentially find anything.
for that. And then, say for example, solve for how long will it take a given object thrown at a given speed or whatever to roll, or to finish sliding, and then eventually roll with slipping, or without slipping.
I guess.
So, we've used torque, forces, kinematics, rotational motion stuff all together. Woo! Yeah. And that's kind of what the AP test eventually will get to work towards, is going to do. Have you, for one problem, pull in all of these different things.
Are they gonna just make up like rules to the universe that
Make up rules to the universe.
like pretend that gravity doesn't exist and this is suddenly happening. Create
Well,
your own
you've
equations.
seen what the AP test kind of asks there, because it's been on your test. All of your tests have become our old AP problems, whether they be multiple choice or free response. So it's not crazy, but I mean, like, like from our last test, right? Who throws a ball up to a ramp that, right, then can suddenly like shift and move? Right?
Physicists.
Physicists, apparently.
We can. Got this crazy moving half pipe if you want to try that.
And you know what? Now, hopefully, you could calculate some stuff about that. And you should feel like, I'm awesome
Hopefully.
with that.
You know, that was always the goal of me taking you.
Yes. Can I calculate the velocity of a moving half pipe?
If Jane drops a piano from it. Glass house.
Or if Jane launches a piano, right, at a certain angle, at a certain
Becoming a
velocity,
cartoon
right?
villain since
And then you
1994.
All kinds of stuff.
The piano is rotating about its end.